So Yiping is here from Northwestern. He joined very, very recently, the beginning of this year, and he works in this general area of data-driven ML AI for science, but specifically around PDEs. And so I think that it would be, Jorge Nosadal suggested that we try to connect, and I think there might be a really good fit in terms of collaboration with our department, since we're so focused on PDEs. So I won't take up any more of your time. Take it away.
Sure. Thanks for the introduction. And today I would like to share some of my recent thoughts. Wants to use like machine learning for the PDE scientific computing things. So first of all, let me apologize for the title because all the words in the title is not familiar to anyone. Because it is like the name created by myself. So I want to go through word by word to specific how does this title means at the first 5 minutes. So this work is actually I have done it for a few years, starting from like my PhD at Stanford, working with my advisors, and recently my co-author at Georgia Tech, Shi Hao, who is a stats background, and my student Ray at U Chicago, who is a applied math master there. So to start with how I go through this project, I would like to go through my research journey a little bit. So start from my undergrad, I tried to work on like using neural network to solve PD kind of problems. So during my undergrad, the thing I'm trying to work on is if I have like a solution in which is the data is from like simulating a PDE. Can we recover the PDE from the data using neural network kind of ways? So to do that, we need to connect two different areas. At that time, they look very, very different. One is like a PDE and another is neural network. So we have these two papers tries to understand neural network are some discretization from the PDEs. For example, the different layers in the neural network, we just understand it from like different time stamp, like longitudinal scheme, different kind of schemes. We build a relationship between numeric ODE and how you stack your layers for your neural network. So this is the first project that I have go through as an undergrad. And another project we try to work on is try to link numerical PDE with the neural network, which we just connect like the convolutional filters in the neural networks with the numerical scheme. So during my undergrad, I tried to connect like numerical PDEs with the neural networks and tries to use neural network for some scientific computing problems. Then I go to Stanford for my graduate study. And there, the things I'm thinking about is, okay, scientific computing always needs numerical analysis to make our result trustworthy. So can we build theory? Can we build numerical analysis for this kind of neural solvers for PDEs? At that time, I tried to build optimal theoretical result for the neural solvers for PDEs or the neural solvers for the operator learnings. I have two papers here to build like the optimality lower bound, upper bound, they matches for everything about the numerical analysis for the neural network for PDEs. Then I started my tenure track job. I just asked myself a question, yes, although I built like theoretical guarantees for neural networks, but do I trust my theorems, right? So for the numerical analysis for numerical PDEs, for finite elements, for finite difference, what we have in the theorem is what we can simulate that. But do I trust the theorem that I have built for AI-based scientific solvers? The answer is definitely not. We have so many assumptions for our AIs. So the assumption is maybe we need to globally optimize your neural network, which means you should globally optimize a non-convex objective function, which nobody can trust this. And then maybe other assumptions is we need some structural assumptions for your PDEs, for the functions you have there. And one of the most funny assumptions made in the CS community is they assume the ReLU function is a smooth function. Can you state your?
Oh, no, ignore that.
Yeah, sure. So it's for the audience there. Okay, sure. So So they even assume that the ReLU function is a smooth functions. So all the assumptions here is not satisfaction. It is not satisfied for building theoretical results for scientific computing. It's not like the case we have seen the success of scientific computing these years using numerical analysis theory to guide the practice of PDE solvers. So for this talk, I want to ask myself a question is it possible to get something I can actually trust? We are actually solving the PDE, but the neural network is still helping here. Okay, so to do this, I just consider how I use ChatGPT every day. Okay, so when you use a ChatGPT, can you trust the result there? No, right? When you ask like your homework question to ChatGPT, you ask your research question to ChatGPT, you can never trust the result there. But what's the thing when you do a ChatGPT? Yes, if you ask your ChatGPT how you can guide you to some place, then you should double check with a map, right? So it's also how you do the homework. You first use the ChatGPT to generate the answer, then you should open your textbook to check whether the ChatGPT's answer follows what it is said in the textbook. So it is said if I want to use ChatGPT for my homework, for my research, what every day I'm doing here is we start from the machine learning solution, but we not end with the machine learning solution. What we do is we should use our knowledge, we should use our scientific thing we have learned every day to correct the answer done by ChatGPT. So I tried this year, I tried to let ChatGPT to prove the lemmas that my students can't prove. The surprising result is it provides the right direction, but it still have a little bit wrong thing there. So we do more detailed error analysis built upon the ChatGPT's proof. So this is every day how you use ChatGPT. You will start from the machine learning solution, but you should use your knowledge and you should use the physics information or everything you have known for your task to correct your AI solution. So this is the talk today. So how we can use the numerical analysis, how we can use the scientific knowledge in hand to correct the AI solution in hand. Okay. So this is actually called inference-time scaling law, which is another word in the AI community. So what does the inference-time scaling law means here? So it is actually a huge difference for the ChatGPT this year and last year. So if you try to ask questions to ChatGPT last year and this year, you will find out that, okay, they give you much better answers. So just trust me, if you tried the ChatGPT 1 year ago, you should try it again this year because it gives you really, really good, much better result. But why? What happened there? The thing happens is they are doing this kind of correction after the LLM's output. So in the last year, what LLM's output is what you have seen on your screen. But for this year, they run something called inference-time algorithms, which is that if once the output once you get some output from the LLM solution, they will still run some searching algorithms to search for better answers. So it is different from last year. They only train the neural network, but this year they also allocate computation when you use the LLM. And the scaling law means that the big companies find out that if you allocate more time during your inference time, which is that if you ask your ChatGPT, it will maybe think for 2 minutes, and there is also another button called deep research, which will make your LLM think for an hour or even half an hour. Then after this half an hour computations, the LLMs can self-correct your answer better and better, and this is what they call inference time scaling. So it looks like the thing I'm saying now is actually inference time scaling. So the question I want to answer today is it possible to use the scientific knowledge in hand to correct your AI solution and to perform inference time scaling? So let me be specific of every word here. So the inference time scaling here, which means that when you train your AI just means surrogate model in scientific computing, I do not allows you to fine-tune or retrain or to train a new surrogate model, which is that the AI you train is just the AI you train there. You can just use the neural network there. You cannot modify your neural network. But I want to use the physics knowledge to embed into that to make it better. Okay, I don't allow you to change the neural network you have trained. So this is the first thing which I said about inference time. Yes, I just assume that you have trained a neural network. I don't know how you train a neural network. I don't know how you get your surrogate model. I just use your surrogate model without modifying it. And for the scientific machine learning here, just means we need to use physics-informed information, which means we will use the PDE knowledge to guide the correction of the neural solutions. Okay, so this is the whole goal of today's talk. And I will first show you two ways to do that. The first way is to do debiasing, and the second way is to do preconditioning. And I want, at the end of the talk, I want to convince you this is a possible way to do that, and the two ways are actually equivalent. Okay, so first of all, I want to say about debiasing. So this is the algorithms, like the big framework I'm trying to build in the last year. Yes, let's consider if you have a function which is the black function f, you want to approximate it. But you use some surrogate model, even finite element or neural network, everything you like, you build a surrogate model which is the f hat. Everybody stop it here for all the scientific computing tasks. But for today, I want to step one step further. Yes, now I want to ask a question is, if I can know how much your neural network doesn't satisfy the physics law, which is that if I can evaluate the error of your surrogate model, is it possible to aggregate the error you have evaluated with your AI solution together to make your AI solution better? Okay, so it sounds possible, right? I know how much error I have made with my AI. This is the information that can make me improve my AI, right? So today is the question is it possible to improve it even without retraining, without fine-tuning, without anything you changes your surrogate model? We just aggregate the error here with your AI solution here, just to use the physics principles, just use first principles. So here is the algorithm framework. We first train a surrogate model. The surrogate model can be finite element, can be neural network, can be Gaussian process, can be tensor network, can be sparse grid. Every method having your numerical textbook, everything can be used here. And then we will correct the trustworthy solver using the physics first principle, the error you have evaluated, to combine them together, use trustworthy solvers. And for today, I'm not using finite element or optimization. Today, I use some stochastic simulation algorithm to show you it is possible to do that. And here is how I will show the numerical result. Yes, the black line here is the error of your surrogate model. But when you do more and more Monte Carlo simulation, more and more Feynman part simulation, you will see that the error will gradually goes down. And finally, you will see the error that you corrected using some Feynman part simulation can be much better than your starting surrogate model. So this is the final goal that I will show you today. Okay. To do that, I would first introduce like a framework how I think about this question. My background is actually from both scientific computing and statistician. So I want to connect these two things together. So the first step I would like to do is I want to reformulate the scientific problem as a machine learning problem. So let me first consider what is machine learning means. The machine learning actually means I have some data x1 to xn, which is sampled from a distribution p theta, parameterized by a parameter theta, right? And once you get this data x1 to xn, I want to recover your parameter theta hat here. So this is all about machine learning, which is we collect some data parameterized by a theta, and we want to recover this theta here. And now for today, let's see how we can characterize that all the scientific computing problem as a machine learning problem. The easiest one is function approximation, right? For the function approximation, if you want to approximate a function f, the thing you can get is the collocation point xi and the function value at the collocation point. Then you can recover all the function f. This is the easiest task we know as supervised learning or function approximation in scientific computing. But let's see, for the numerical PDE, I can also formulate as that. So for the numerical PDE, you can see if I want to solve the equation Laplace u equals to f, so let's just ignore the boundary condition, consider the easiest case. So for Laplace u equals to f, the thing you can do is you can have a collocation point x here and knows what is the function value of your f at this collocation point. So this is your data set. And the data set is actually parameterized by the solution U, which means you just parameterize everything by the Laplace inverse of your f, and the information you can get is just the collocation point and the function value of your f. Then you can formulate everything as a machine learning problem. And for the numerical linear algebra, it's also the same. For the numerical linear algebra, the true information is the matrix A. I know nothing about it. But the thing I can actually do is I have a vector. I can multiply my matrix with the vector. So I can do matrix and the vector multiplication, right? So the matrix and the vector multiplication is the only way in numerical linear algebra that enables you to get the information of your A, and you want to do everything here about your A. So now I try first to this is trivial, I know. So I just try to connect like all the scientific computing tasks as a machine learning task. So this is like my my graduate research wants to do is based on this kind of reformulation, we can transfer all the solutions from the stats community to the scientific computing community to see whether the understanding from the stats community matches the understanding from our scientific computing community. And some surprising things comes out is actually these two things are not aligned. So there are many of the conclusions here. If you use these links, you will find the two communities will have very different conclusions. Then you need to understand the discrepancy here. But for today, I will do one step further. So the one step further is I will also consider some downstream applications. So what does the downstream applications here means? So for example, I want to do function approximation, but the task I need to know here is not all the information of your function. I just need to know some moments which represents the velocity, which means the quality design, or means some temperature here. I just need you to return some moment function here. And for the PDEs, maybe I just need you to know the PDE solution at the origin or at some given space point, which is an important application in high-dimensional PDEs. Because for high-dimensional PDEs, one of the applications is control. You just need to know the control at a given point. You doesn't need to know the control at every point. So I just want to know what is the PDE solution at a given space point. And for the numerical linear algebra, there are cases that you just need to know the trace, or you just need to know the eigenvalues, right? So now we consider one step further, is we just need you to know how like this kind of downstream application. I want to do function approximation. I just need to know the mean or moments. If I want to have your PDEs, I just need to get to know like at your given space point. For the numerical linear algebra, I just need to know what is the trace or eigenvalues. In these kind of applications, can we design better algorithms? So this is my today's task wants to show you. Okay. So to do this, the thing I would like to say is, okay, now I have a surrogate model, which is a theta hat, right? As I said, I know nothing about my theta hat. The theta hat may be good, may be bad. And the thing we know is we want to do the phi theta hat estimation. So today's numerical task is how we can estimate the phi theta without knowing an unbiased estimation theta, which is that we want to know unbiased estimation of your phi theta, even with a biased surrogate model theta hat here. So it looks like a magic thing, which is that I want to do unbiased prediction, even with a biased machine learning estimator. But the thing actually mathematically is quite easy. If you want to estimate the phi theta, the only thing you need to estimate is actually the difference between phi theta hat and phi theta. Because theta hat is the surrogate model you have in your hand, so you can compute out what is your phi theta hat, right? So then if you want to know what is your phi theta, the only thing you need to compute out is the difference between phi theta hat and phi theta. So this is all the things I have said so magically, which I don't change the theta hat. I can do the correction. So if you want to do the correction, the only thing you need to compute out is this phi theta hat minus phi theta. This is the easiest math of like my talk today. And for today, I will show you it is possible to use some kind of physics information or first principle-based method to do stochastic simulation, Brownian motion simulation, Monte Carlo estimation of this kind of quantity here. Okay, so today's talk is just about these two parts. I want to convince you. The first of all, why I can estimate this, it is because we are physics informed. We have the first principle, so we can do Monte Carlo simulation using the structure of the functional phi here. And why it is easier, why we still need the theta hat here to help us, because today I just use the neural network as a variance reductor. I don't use the neural network as something directly gives you the answer. I just use the neural network as a variance reductor, which makes your numerical simulation easier. Okay? So here is the 3 tasks I will show you today. In both of the applications, I can build new algorithms, new solvers. The easiest one is the numerical analysis 101 task, compute the quadrature. And the PDE solver, like the benchmark task we have in the PMS community, and eigenvalue solvers. In both these 3 new applications, I can show you new algorithms, new solvers, new ideas. Okay? And firstly, I would like to say about the numerical quadrature. So we can directly go to the quadrature algorithms. So for the numerical quadrature, which we know in the textbook, right? So in the numerical analysis, the first class when we talk about quadrature rule, we'll say about Simpson's rule, right? So what does Simpson's rule means? If I want to compute out the mean of a function, what is the Simpson's rule doing? The Simpson's rule will say, okay, let's first build a piecewise polynomial or piecewise linear approximation to our function. Then we just compute out the mean of the piecewise linear approximation, right? So this is how Simpson's rule working. And for today, we just consider this piecewise linear or piecewise polynomial approximation as a surrogate model, okay? Which is that the algorithm we have in our numerical analysis textbook is that we have this black function, we want to compute out the mean, but the only thing I can get is like approximated function f hat, the gray dot function here. And we want to compute out what is the mean, we approximate that with the mean of these gray dot functions, right? Okay, so now for today's task is that I don't trust this because maybe your function approximator here is not a good one. So now we need to correct the answer here. And how we can correct the answer here? So it is that we know the thing we can get in hand is this function approximator's mean. So we need to know what is the difference, right? We need to know what is the difference between the function and the gray dot functions. So this is how I do that. Is now I use a Monte Carlo solver. I just randomly sample some collocation point, and at each of the collocation point, I can know the function value and the gray dot function's value, which is a surrogate model's value. So which means that I can randomly select some collocation point, and at each of the collocation point, I can tell you what is the error of your function approximation, right? So now the algorithm here is such an easy algorithms. We start from the Simpson's rule. And we don't end with the Simpson's rules estimation. We correct it by sampling a new random collocation point. And on these random collocation points, I just evaluate how much you have to do wrong about your function approximation, right? So first of all, you may trust that this is a better algorithm than Simpson's rule because we start from the Simpson's rule by doing a correction, right? So this must be better than the Simpson's rule. Maybe your question here you want to ask is why it is easier, better than just doing Monte Carlo, right? You can just have this random collocation point and compute out the function value and to get like a Monte Carlo estimation of your function mean, and why my algorithm is better than this. So the reason is if you look at the function value get here, the variance here is actually a constant because the variance here is the variance of you sampling the functions. The function value is always an O1 thing, so you will have O1 variance here. But in my algorithms, I just sampling these kind of residues. The residues are small because if your function approximator is good, the residues should be small, right? So I'm just randomly sampling this kind of small residues. Then the variance here should be really, really small, right? The variance here is large, but the variance here is much smaller. So in a variance reduction sense, our algorithm have much more smaller variance than directly to the Monte Carlo. So this actually comes out a really interesting conclusion at this point is during my undergrad. So the big name at our department is Weinan. So Weinan has always taught us, okay, if you are a low dimensional problem, you go to Simpson's rule. If you are a high dimensional problem, you go to Monte Carlo algorithms. So it looks like everybody is saying the Simpson's rule is better for low dimensional smooth problems, and Monte Carlo is good for high dimensional rough problems. So this is the education I have during my undergrad. But this research just renews my understanding is I constructed out an algorithm which is better than both Simpson's rule and Monte Carlo algorithm. by combining them together. So it is not like the Simpson's rule or the quadrature rule and the Monte Carlo algorithm should be competitor. But the truth is, if you combine them together, you can easily get an algorithm is better than both. Okay? So if you comes from different community, it is not our new algorithms. If you comes from a stochastic simulation, that algorithm is actually called regression and adjusted control variate. So if you are from economic department, their name is called doubly robust estimator, which is I have two estimators and I combine them together, you can always get a better algorithm. So in the economic department, they call it doubly robust estimator. And if you are from engineering departments, then Karen Wilcox and Benjamin Rothkopf, they have a paper called multi-fidelity Monte Carlo, which is almost the same as my algorithm here, but have slightly different setting of the surrogate models. So you will ask a question, so what is your contribution here, right? So all these algorithms are very, very similar. So the interesting thing is, in our newest paper, we can actually prove that this algorithm is the optimal algorithms to solve the quadrature rule, which is that no algorithms can have faster convergence rate than these algorithms. So the best algorithm to do quadrature rule is to combine them together. Because I want to introduce my new algorithms on PDEs and other applications, so I don't have time to do that. So I just shows you I have a lower bound proof, I have an upper bound proof. Okay, so I don't need a slide just to convince you I have the complicated proof, and the upper bound and the lower bound matches with each other. And this tells us this is the optimal algorithms, but I have a take-home message on the theory. It is not always the case the algorithm combining the Monte Carlo and the Simpson's rule is the best answer. It is the optimal result. It should depend whether you have a real event. So our theory says that if there is no real event, or the real event, the definition is infinite variance. So if you don't have infinite variance real event, then the optimal answer should be start from the Simpson's rule and use Monte Carlo algorithm to correct that. But if you have a real and extreme event, all the effort is you need to deal with like these real events. So if you have a real event, the only thing you can do is to truncate it, right? To truncate it, and if you have more information, then the truncation can be larger. You have more and more samples, the truncation will become much larger. So this is the only hardness for dealing with this kind of real events. The smoothing will no longer help you in terms of the convergence rate. It will still help you in terms of like constant, but it will not improve like the convergence rate. So this is like the main take-home message for you is if your problem in hand don't have infinite variance, it's always good to build like a very rough Simpson's rule and then to build a Monte Carlo solver on that. So this is the first example, easiest example. I want to convince you this kind of methodology actually works is we start from a surrogate model and we use a Monte Carlo algorithm to evaluate how much error I have made for my surrogate model and then correct it. And even I can show you the statistical optimality. Okay. So this is our paper here at Europe's 23, and I will use the same idea for the PDE solver. Okay, so for the PDE solver, we also still have this kind of two-step, like the machine learning part, who is the downstream application part. For the machine learning part, what you will have is the collocation point of your right-hand side function to recover your PDE solution. At this step, I don't constrain the method you use. You can use Garotti method, you can use sparse grid, you can use tensor network, you can use neural network. I don't constrain how you do in your first stage, but let's consider what's the procedure here. The procedure here is we know the true function should satisfy Laplace U equals to M, right? And now I have an approximate solution. I write that down as U hat. U hat is your surrogate model, is the PD solution you get in hand now. Then I do a magic step, is I use the first equation to minus the second equation. And because my Laplace here is a linear operator, right? Then the Laplace of U minus U hat will equals to F minus F hat. Then, which is that if I can solve out this equation again, then this U of U hat can correct my U hat solution to get a better PDE solver, right? So I will do the same thing. I use a Monte Carlo solver here, which is that if I want to solve the Laplace U equals to U minus U hat equals F to my F hat, the only thing I need to do is I sample a Brownian motion. I sample a Brownian motion, and I collect all of the function value of f minus f hat during this Brownian path. Then this is the solution of my PDE, right? So the algorithm here is such an easy algorithm. You start from any solution you get from your co-author, then he will give you like a surrogate model of the PDE solution. Then you just run a Brownian motion, and during the Brownian motion, you collected how much the PDE is deviate from the physics principle, and then aggregate the information to your PDE solver. Then you can collect all the information. And why this is better than directly run the Monte Carlo algorithm is the same. If you directly run the Monte Carlo algorithms, then the information you need to collect here is the value of your f, right? But now the value I collected here is f minus f hat. The f hat is a good approximation to f, so f minus f hat is small. So all the variance along the path here is small. All the solver here have much better complexity here. Okay. So you may say, okay, Yiping, the story here looks nice, but you are utilizing a linear PDE, right? Can you do nonlinear PDEs? So the answer here is I can do nonlinear PDEs. It is because I can just need like semi-linear structure. It is because if you want to run this stochastic simulation, see, the only thing you are utilizing is you have a diffusion term. If you have a linear diffusion term, then you can simulate everything here easily. So I will show you can do that for the semi-linear PDE again. So if you have a semi-linear PDE, then you say, okay, I have a neural network, which is a U hat, I plug that in and get an error here of GXT. Then you do the same thing. You just use the first equation to minus the second equation to get a new equation here. Because all the first two terms are corresponding to the diffusion, it is linear. So all the linear structure here kicks out. And all the magic thing here is I just put all the nonlinear terms here as a newly nonlinear term. I don't know how these kind of nasty things here together. I just deal with that with a new nonlinear term. So you will see because of the diffusion terms is a linear thing, so all the semi-linear structure here is inherent. So you can see all the things here is still a semi-linear PDEs. You can still use the Monte Carlo algorithm to do that. And the Monte Carlo algorithm to do this is called multi-level Picard iteration, which is that I want to solve the semi-linear PDE. I use a Picard iteration to solve that. And at each iteration, I do a Feynman part simulation. So this is the basic idea to solve this kind of PDE using Monte Carlo. So in most of the older cases, our PDE, we simulate the PDE to 100 or even 200 dimensions. And in all of the dimension, and for the first one is like the first one is a linear simulation, and the second to a Burger's equation with velocity, and this is the control theory equation, and this is the diffusion reaction. So for all of my numerical experiment, you can see if you do a correction, you can almost like half to have like 50% improvement of the error by simulating about 1,000 Brownian process. Then you can easily half your surrogate model error. Okay, so this is the thing I want to show you. Is it also have like inference-time scaling behavior, which is that if you have like more and more iterations of the Picard iterations, then the improvement will become better and better. So all our experiment shows here, we just run three iterations of Picard iterations, then it can improve almost a half. And it is also the same thing as the previous work. Is if your surrogate model or finite element or neural network method have a convergence rate and smoothness over dimension, your Monte Carlo rate have another Monte Carlo rate convergence here. So why here is not half? It is because if you want to simulate high dimensional nonlinear PDEs, you need to do branching process simulation. So we don't have half convergence rate here. So if you have like these two different kind of methods, you combine them together, you can get a faster convergence rate than both by times them together. So here is half, here is S over D. You just time them together to get a better rate. So this is the reason why we can have this kind of better rate, and we can even we can even simulate this in the real case. Is we use different training size and corresponding Brownian motion process. We can see once you add this correction process, you will have like a faster convergence rate than the direct Gaussian process surrogate model. So if you want to know why we have like this kind of better convergence rate, it is because the surrogate model here, if your surrogate model have a convergence rate at n to the gamma's power, which is that in your simulation, the variance is at the n to the negative gamma's power level, then you will do another Monte Carlo simulation. Then you will times these two things together to get a better convergence rate. Okay, so this is the thing we proved and numerically validated thing is you can start from a PDE surrogate model and then use a Monte Carlo solver to iteratively improve your estimation here. So this is our paper. We just put it on archive. We have like a code open on GitHub. So if you want to play with it, is you can. I'm always happy for feedbacks. And for today, what I show you is in all the literature, everybody is debating about two extremes. The first extreme is if your neural network is good, you just give the neural network solution. But there are still mathematicians don't trust neural network. What they said is, well, your neural network is bad in my applications. I just want to do numerical simulation. But for today, I show you a marriage. Yes, okay, you have a neural network solution. I don't know if it is good or bad for my applications. I just say, okay, it's okay for my application. Then I use the numerical simulation to calibrate the machine learning result here. And there are possibility lies in between, which is that combination of the both algorithm to get even a faster convergence rate. Okay. So another interesting thing I would like to say is my algorithm here is also a multi-scale algorithm. Why? It is because in our functions, we always can decompose that into coarse scale and fine scales. Coarse scales are smooth functions. So the smoothness can be easily captured by a surrogate model because the surrogate model is just utilizing the smoothness information, right? And for the fine scales here, we use Monte Carlo algorithm to capture the fine scales oscillating information. And why we capture here using the Monte Carlo algorithms, it is because the Monte Carlo algorithm is the only algorithms I know in the textbook, which is that the complexity don't relate on the smoothness. So if you consider what is the complexity of the Monte Carlo algorithm, it is the variance and bounded by the moments, right? So for the Monte Carlo algorithm, it is only depend on the magnitude of your function, but don't depend on the regularity of your function. So we decompose our function into two parts. The first part is only about the smoothness, about the regularity, and the second part is nothing about the regularity, but which is just small oscillations. That is, everything has small magnitude and easy to simulate. Okay. So I would like to say, not just the work I have shown you today. There are many algorithms, even in numerical linear algebra, can be concluded in this framework, which is a trace estimator. So for estimating the trace, the best estimator is called Hutchinson++, which is proposed by Li Lin at Berkeley, Mass. 2017, and recently 2020 it is proved by Musko and David Woodruff at CMU and NYU. Yes, they have a joint work together to prove this estimator is actually the optimal algorithm for trace estimation. And their idea is they first use randomized SVD to get an estimation of your A, and then they estimate the trace of A minus A hat using the Hutchinson's estimator, which is the Monte Carlo estimator of the trace, to correct the solution that is there. And this algorithm is proposed by Li Lin and recently proved it is the optimal algorithms. And they apply that in graph theory, quantum theory, and many places here. So this is not a complete list. I'm trying to write down a framework paper. So I'm lazy. I'm writing that. The students are working hard. So all the applications paper are already out. So this framework paper, I can conclude many algorithms from different literature into this framework to conclude everything. I start from the surrogate model and then correct it using the physics information. Okay. So the next 15 minutes, I still have 20 minutes. So I want to say about precondition. Here is our premise department. I don't need to convince you is the thing we know here. All the things, if I want to conclude in all the things I have talked about is I have an approximate solver. I want to use the approximate solver to improve my solver, right? So this is everything I have said about. But if we are prime math background, the naive solution we will have here is to do the precondition, right? So if I have approximate solver, the everything I will set, I was taught during undergrad is if you have a like approximate solver, you need to use your approximate solver as the preconditioner, right? So this is how we develop the multigrid. So for the multigrid, it is approximate solver. We never use it as a direct solver, but we use the multigrid as a preconditioner for a CGE algorithm, right? So this is all about to use approximate solver as a preconditioner. So why you do it in a debiasing way, which is very, very different from what we have seen for in the numerical literature. So for today, I will show you these two ways are actually equivalent. It is actually a very, very surprising discovery. Yes. So let's have a review. What does preconditioner mean? So the preconditioner says that if I want to solve AX equals to B, the A is a large, hard matrix. I don't know how I can solve that. Then I just get an approximate solver, which is called B. I inverse my B before my equation. Then this is the precondition, the version of my equation, and I want to solve that, right? So this is the preconditional means. Let's go through what is the algorithm I have said about today. So the thing I have said about today is, okay, you have approximate solver here is B. So the solution here is x1. Then the thing I will do here is I minus like AX equals to B with AX1, right? So then you can reconstruct a new equation here, which is A times X minus X1 equals to B minus AX1. So it is just iterative refinement, right? So nothing new, iterative refinement. So the thing different from iterative refinement is I use approximate solver to solve it again, right? I use approximate solver B to solve the equation again to get an x2 as approximation of x minus x1 to correct the solution x1. So this is easier to solve because B minus AX1 is small. The x2 is in a very small scale, so you can get the estimation correctly easier. Okay, and you can change that into an iterative algorithm. Once you have a solution, I can correct it. You have a solution, I can correct it. It is an iterative refinement algorithms. So this is the algorithm I have set today, right? It is I have an equation. I just write down what is iterative refinement kind of method to iterative refine it. So this is the algorithm I have set today. And this observation I will contribute to my student Rehan at U Chicago. One day he told me he write down the iteration and he find out that it is equivalent as the precondition Jacobi iteration. So it is that if you do this procedure, you're actually just simulating this kind of procedure. Okay, so which is that in the linear case, we can do the debiasing and the precondition, they are actually equivalent, which is that if you do this debiasing step by step, it is almost the same as you do a precondition Jacobi iteration. Okay, but the good thing is the debiasing way can be easier extended to nonlinear equations. So for today, I will show you is we use debiasing as a new way to implement precondition, which is a thing we don't know how we can do that for the linear equations. Yes, we have an equation A u equals to B, potentially nonlinear, but we have a approximate solver can let A u have approximately equals to B. Then we use this kind of iterative refinement way to improve that. Okay, so we just to iterative debiasing a new learned solution. And it is equivalent to use the approximate solver as a precondition. So let me show you the example by numerical linear algebra. So for the numerical linear algebra, the literature here I would like to go through is a randomized numerical linear algebra, which is I thought that A matrix here is a large matrix, but we use the idea from machine learning, which is that we randomly sample some columns and rows. These kind of things will capture most of the information of my matrix. So everybody now doing here in the numerical linear algebra literature, it is that, okay, let's randomly sample some row and columns of my matrix A, and we can reconstruct my matrix A by using the randomized SVD or other sketching algorithm, Gaussian sketching, sparse sketching, randomized SVD. We just use these kind of things to get an approximate A hat here. And if you want to build an approximate solver about least square solver or eigenvalue solvers, then you just replace your A by your A hat. So this is the randomized SVD. Let's consider what is randomized SVD doing. I have a big matrix. I project that onto a random subspace, compute the SVD over the random subspaces, right? So this is exactly the procedure now for the randomized numerical linear algebra. So they call this kind of approach as sketch and solve, which is that I have a matrix, I sketch it, and directly compute everything on the sketched matrix, solve the original equation on the sketched matrix. So this is exactly the sketch and solve. And for today, I will start from sketch and solve to iteratively refine the solution by a debiasing way to construct the sketch and precondition algorithms. Okay, so this is the thing I want to do here. So all the things here I have done in the previous talk is based on the linearity of the phi so that I can do Monte Carlo solvers, right? So I know how I can deal with the linear solvers, linear phi's, but I don't know how I can deal with the nonlinear phi's. Then the thing is, if you want to do nonlinear things, you just need to do a Taylor expansion, right? So we can approximate this phi theta hat minus phi theta by the Taylor expansion term, which is the linear approximation of this nonlinear functional, right? Then we just do the approximation to this Taylor expansion terms, which will give you like the answer. So you have two parts here in the Taylor expansion. The first thing is the error of your theta, right? The theta hat minus theta. And the another thing is the Jacobian matrix here. So you will use the structure you will have in your algorithm is the Jacobian matrix times like this theta hat minus theta here. And it is actually very, very similar to a Newton step because this looks like a gradient and this looks like a H inverse. So they have some kind of relationship. I will say that later. But let's just start with this, try to work on eigenvalue problems, okay? So now we have like a approximate matrix A hat. I want to correct my A hat eigenvalue estimation. What's the algorithm we will get? So our method is look like here. So we write down what is theta minus theta hat. So it is A minus A hat, right? And this is the Jacobian matrix, which looks very, very similar as the inverse power method, which is the lambda I minus A inverse. This is exactly the same thing, looks like the inverse power method, but the only difference is here because we are following the Taylor expansion structure. So here we are doing theta minus theta hat. So what is the good thing of our iteration than the inverse power method? So let's consider if you run an inverse power method, you change your A to an approximate solver, which is that I change my A to an A hat. Then you are converted to a wrong solution. You are converted to the eigenvalue of your A hat, right? You are not converted to the eigenvalue of A. But if you change the A to the A hat here, no matter which A hat you are selecting, you always converge to the true eigenvalue of A. Let me show you that. So if your xn is the eigenvalue of your A, then Ax gives you lambda I. A hat gives you A hat, and here is inverse, so these two terms cancels out, right? So in our solvers, no matter how you select your A hat, the iteration will always converges to the true eigenvalue, but not the approximate solver, right? So this gives you a really good thing is the true eigenvalue is always the fixed point, but if you replace the solver in the inverse power method to approximate solver, you will change the fixed point. Okay, so this is another reason that my A hat is actually serves as a preconditioner. It is that no matter how you select your preconditioner, you always converge to the true solution. The thing is, if you have a good approximation of your approximate solver, it will converge faster. We can prove similar thing for our algorithm. Okay, so the first take-home message is because we are doing debiasing, so you should follow the gradient times Taylor expansion result. So you should power the residue, but not power the vectors. So this is like how I would like to summarize my work in the literature is in all the literatures, what we need to do is for the eigenvalue problems, they just do sketch and solve. So which is that I have like a random projection of the matrix and directly solve SVD on the random subspace. But today I would like to do sketch and precondition. I use the approximate solver just like a precondition, but I don't use that as like as an approximate solver. But maybe you also have the question, I'm convinced no matter how you select A hat, you will always converge to the true solution, but don't know why better A hat gives you better convergence rate. So this is another interesting observation from my side is it is actually using Newton method to solve the Lagrange form. So if you write down the eigenvalue problem, go through the Lagrange form and write down the Newton method, it is exactly the same as our algorithm. Okay, so this is another interpretation we find out later after we write down the algorithm here. Okay, so I would like to show you some numerical experiment here. So we compare our method with inexact inverse iteration, inexact inverse inverse iteration and the Davidson method. Our method is faster, definitely. Otherwise, we will not write the paper. But it is also much more robust. So we run it on 550 different random the matrix, and you can see ours have like a much smaller errors here. So this is something I don't understand now, but it looks like our algorithm is much more stable than the direct Newton method. Okay, so this is our paper just archived and updated just last Friday. And another surprising fact here, actually surprised us a lot, is the iteration I have constructed will always lies in the curl subspace. So it looks like we are just a curl method, but why we are so surprised or so excited about this fact here? It is because if we just have like dynamic system data, which is that we don't know the matrix A, we just collect data from our dynamic system, then the only information you have is your curl subspace, right? So all the estimation you can do is just the information in the curl subspace. So our algorithm can even be extended to dynamic mode decomposition. Not every algorithm can be extended to dynamical mode decomposition because of these curl subspace constraint. For example, the randomized SVD algorithm. It is very hard to extend that version to the dynamic mode decomposition. But our algorithm can be easily extended to the dynamic mode decomposition because of the fact is our iteration lies in the curl subspace. So we can do dynamic mode decomposition. We can do online faster update. I will say it later. Okay. So what does the online update means? So if you consider our algorithm for DMD, what is it actually working? So for the dynamic mode decomposition, what you do is you collect all the all the dynamic system data in the history and estimate the mode and do the future state prediction, right? This is all dynamic mode decomposition about. But for our algorithms, we are doing an interesting thing is we will at a new time, you will see a new feedback, right? At time t+1, you can collect a new data from your experiment. Then we compare the new data from the experiment with the prediction together. Then we measure how much your estimation is different from the ground truth, and we use that as a feedback to update your mode estimation. So it is like we are using the feedback as an information to step-by-step correct your mode estimation here. So we try this on the true data. So on the true data, you can see our mode estimation will always improving when you collect more data. But for the dynamic mode decomposition, it is not always improving. The reason is here. So you consider how the dynamic mode decomposition selects the embedding. It selects the embedding as the top singular vector space of your data, right? When you collect more and more data, your dynamic system goes to some stationary. Then if you collect more and more data, the top eigenspaces are not changing. So you actually constrain yourself by doing the SVD or by selecting subspaces. But our algorithm is not. Our algorithm is how much you have to do the error, then you correct it on the information. We don't let us to license this kind of top eigenspaces. So we get rid of this kind of top eigenspace constraints, so we can always improve our algorithms here to the naive dynamic mode decomposition. And the second good thing is in our new equation, although there is a matrix inverse, but we do a clever thing is we compute out what is the orthogonal basis for the modes. Then we only need to do a QR decomposition. Then no matrix inverse, even no SVD computation. So if you want to rerun our dynamic mode decomposition, you need to rerun a heavy SVD over all your data, right? But in our computation, we have no matrix inverse, no SVD. The only thing is you should need to know what is the the orthogonal basis of your eigenspace. So you just need to run a very small n times r QR decomposition, then everything can be live in a closed form. So we just have matrix and vector multiplication in our algorithms. Okay, so we can collect all the things. So if you do direct DMD prediction, because you are constraining all your prediction to the top eigenspaces, then this kind of artificial tail is very hard to remove in the tube flow. But in our estimation, we can easily remove out this kind of artifacts. Okay, so another interesting thing is we actually build a connection between iterative debiasing with the Newton method. Newton method is very easy for the convergence analysis, but it is really hard to do numerical stability analysis for the Newton method. But in the iterative debiasing, the framework itself is really nature to do the stability analysis. So based on this, we do the first numerical stability analysis for the randomized least square solvers. So we propose one of the first backward stable randomized iterative solver. Here is our paper just published at ASDAT 2025, but I don't have time to go through the details. So here is what I want to talk about today. Is we just start from like a surrogate model and we collect the feedback or error by using a new data set and use that to do like actually an update. So I still have 5 minutes. I want to introduce all the literature and my research philosophy and all the other projects I'm trying to work on so that we can have cooperation here at Northwestern. So this is actually the research philosophy I have here. I work on different areas. I have advisors from different areas. So I want to conclude everything using the same philosophy, both machine learning, PDE solver, and numerical linear algebra. So that I want to see how the techniques in different areas can be transferred to another area. So for today, it's actually a good examples here. Is we first show you the upper bound and the lower bound analysis can be transferred from machine learning to PDE solver and numerical linear algebra to see even textbook quadrature rule algorithms are not optimal. We can improve that, right? And from the algorithm perspective, we can start from like this scatter and solve and sketch and precondition difference to refute algorithm in PDE solver and machine learning, how we can translate back from this area. So this is actually my philosophy. I have background from both stats, applied probability, numerical analysis, numerical linear algebra. So I want to see how the different concepts are connected in different areas so that we can combine that together to build new solvers. And here are the things I also want to introduce to you because we are the expert from the FMS community. So here are definitely projects that I need your help and are interesting here. The first thing is I'm also working on multi-scale analysis here. So as a topic analysis, I want to work on is the gradient flow approximation to the gradient descent. So everybody will think the gradient descent as an approximation to the gradient flow, but I want to tell you the story is wrong. The story is if you do gradient flow, so if you have like a minimizers, the minimizers is a manifold. Then if you do gradient flow, it will go to the manifold directly and stops here. But if you run the true gradient descent, you will find out that the gradient descent, because it has oscillation, it is finite step size, then the gradient descent will move along the stationary manifold. So this is actually a phenomenon none of the optimization experts can explain. So I'm trying to write that down as a boundary layer analysis. So we do the isentropic analysis respected to your step size to understand that as a velocity. Then you can see the average behavior. It can be written down as a boundary layer, which can characterize the moving direction over the stationary manifold. So we want to connect like this optimization phenomenon using this kind of multi-scale analysis of approaches to see how the gradient descent dynamics is actually moving through the stationary manifold. I know the department here is really strong at multi-scale analysis. I actually faces some problem doing the multi-scale like expansion here. So if you are interested in this kind of problem, I'm always interested to talk with you. And another interesting project I want to tell you is actually the neural network solver for the PDEs. So I know many of you are well against this, but I'm also like against her 1 year ago. 1 year ago, I still remember my advisor told me only solve high dimensional PD using neural network, never touch turbulence using neural networks. So this is his last words to me during my graduation. But things are changing. Today I want to show so this is like a very preliminary result here from me and my co-authors. Yes, we actually find out that the hardest of using neural network to solving PD is the optimizer. So we change this optimizer so that if you have a larger and larger neural network, the result can even improve into the machine precision. So now for the common flow at the random number 10,000, we can trace the neural network to machine precision using a not large neural network. So here is the result we get. Here is the spectrum we estimated. So I want to show you there are actually some room of like a harder problems. If you have in hand, you think harder to solve using the spectral method or finite element, I would like to try using the neural network because this is the first time we go to the machine precision. All the previous work I saw, they can't go to the machine precision and nobody knows why. And today we comes up with a new neural network optimization algorithm that can do better and better for wider and wider network and go to the machine precisions. And I'm also interested in like operator learning. Andrew Stewart gave a talk last year here. And another interesting thing that also motivates you is I'm also working on the infinitely deep and wide neural network limit, which is limits the neural network in the mean field limit and limits the neural network in infinite depth goes to ODE. So it is like ODE model with a mean field interaction between each of the neurons. So if you're interested in any of the project, I'm here. I'm always here at Northwestern for you to discuss about. Yeah, I think this is all about my today's talk.
So I know we're at time, so if anybody needs to leave, go ahead. But are there any questions?
Yeah.
Go ahead.
So one question I had was about one thing that came to mind as you were talking about this in terms of debiasing is like a chaotic system. Have you thought about, does this debiasing work in that case where you don't have
Yeah, so we are not dealing with chaotic because we also always have a diffusion, right? For the chaotic system, I don't know whether there is actually a Monte Carlo solver. So if we have a Monte Carlo solver, I can design that. So the trickiest thing of my talk here is, although it looks like a nice story, but you should do case by case study. So it should depend on the equation and the solver you have in hand, and I need to utilize the structure of the equation. Yeah.
Did you have a question? No. I'm curious,
Mhm.
what is currently limiting the error on the correction? Like if you kept doing the correction, do you keep improving or is it bottoming out?
It will bothers me. So here is actually something here. So the thing actually bothers me is here. So I'm saying if you have a better machine learning model, it will also have like a better correction result, right? But the thing I don't tell you is what does the better here means. The better here in theory, I can prove is for L infinity convergence. The better means the L infinity error. Do you believe a neural network can provide the L infinity approximation? I don't believe that. So the thing here is the thing is good for precondition and the debiasing is not the same criteria as good for machine learning. So these criteria still have a gap, and I don't know different algorithms will have different criteria for good approximator here. So this is the thing I'm still wants to study. Yeah.
In your error, are you approaching the limit of like the numerical
No,
method?
no.
Nothing.
Oh, but it is 100 dimensional PDE. Nobody knows what is the limit there. Yeah.
Well, let's think Yiping again.